Today we are going to discuss about 4-bit synchronous decade counter. So what is meant by a decade counter? Synchronous means we know that a single clock pulse is given to all flip-flops. What is meant by a decade flip-flop? This is the state of a BCD or decade flip-flop or counter. That is, there are 4-bit counter. So here there are 4 stages are there: Q0, Q1, Q2, Q3. There are 4 outputs. Outputs are there, and initially all outputs are set to 0. Then is 0 0. Next clock pulse. This indicates the clock pulse. There are decade counter. It has 10 stages. It starts from 0 to 9. So there are initial state is 0, then 1, 0 0 1 0, then 0 0 1 1 up to 1 0 0 1. That is indicates 9. And after that, next clock pulse, the state will be 0 0 0. So there are total 10 states are there. It starts from 0 to 9. So how to draw a logic diagram for a decade counter? We know that here there are 4 outputs are there, or it's a 4-bit synchronous counter. It is 4-bit synchronous counter. So how many flip-flops are required? There are 4 flip-flops are required. Then here we are using JK flip-flops. So first look at the Q0. In Q0, we know that the Q0 output changes every clock pulse. So J and K values of the first clock pulse is connected to 1. So it complements or it toggles every clock pulse. So Q0 is changes in every clock pulse. It from 0 to 1, then again 1 to 0. So the JK value for that flip-flop will be 1. Then next, when will Q1 changes? Here Q1 changes here when Q0 is 1. The next clock pulse Q2 changes from 0 to 1. Again when Q1 is equal to 1, the next clock pulse it changes to 1 to 0. So whenever Q0 is 1, then on the next clock pulse Q1 changes its stage. When reaches here 1 to 0, but when here it reaches Q0 is 1, on the 10th clock pulse the Q1 doesn't change. So we need an addition condition, that is whenever Q3 is 0, when Q0 is 1 and Q3 is 1, it will not changes. But when Q0 is equal to 0, Q3 is equal to 0, at that time whenever Q3 is equal to 0, then Q3 is equal to 0 and Q0 is equal to 1, then it changes the state. Q1 changes the state, otherwise it will not change. So Q0 is equal to 1 and Q3 is equal to 0. So the condition is Q0 Q3 bar. So whenever the input of JK in flip-flop is Q0 Q3 bar, then that time Q1 changes. The next case, whenever Q2 changes when Q1 is equal to Q1 and Q0 both are 1. Q1 and Q0 both are 1. Then on the next clock pulse Q2 is changes from one state to another. Whenever Q1 and Q0 1, then Q2 changes. So the third flip-flop Q2, output of Q2 changes when Q1 and Q0 both are Q1 and Q0 both are 1. So both are 1, then it changes. So it is connected to an and that input is given to, output is given to JK flip-flop, then it will be changes. And last case, when the next case, when Q3 is changes. Q3 changes when Q3, Q2, Q1 and Q0. Q2, Q1, Q0. Both are, all these three are 1. Then Q3 changes from opposite one state to another. Then again, when we look at this 10th clock cycle, after 9, it will be changed to 0. So what will be this condition? Here Q0 and Q3 both are 1. Then also Q3 changes to one from one state to another state. So these are the two conditions. So the JK value will be, what will be the value? Q2, Q1, Q0 plus Q0, Q3. Any one of this condition is satisfied, then Q3 state changes from one state to another. So that will be explained here. In this case, first case, the first flip-flop Q0 toggles on each clock pulse, and on each clock pulse, so J and K inputs are equal to 1, and J0 and K0 is connected to 1, and the second flip-flop Q1 changes on the next clock pulse each time Q0 and Q0 is equal to 1 and Q3 is equal to 0. So J and K1 value will be Q0, Q3 bar. Q3 is equal to 0, so it is Q3 bar. Equation becomes Q3 bar. So it is connected to and it is given to the J and K1 inputs of flip-flop. Then flip-flop 2, that is Q2 changes on the next clock pulse of Q1 when Q0 and Q1 both are 1. So J and K2 value will be Q0 into Q1. And this Q0 and Q1 are and it is given, this gate output will be given to J2 and K2 input of flip-flop 2. Then when if flip-flop 3, Q3 is changes to the opposite state on the next clock pulse each time Q0, Q1 and Q2 both all these three outputs are equal to 1, that is state 7. And also, or when Q0 and Q3 is equal to 1. So this equation becomes J3 is equal to K3 is equal to Q0, Q1, Q2 plus Q0, Q3. Here this is the AND operation, and here we applied AND operation. Sorry, here OR operation. Plus indicate OR and Q0 into Q3 indicates AND operation. This is the logical diagram of a 4-bit synchronous counter. We require 4 bits. It is a 4-bit synchronous counter. So there are 4 flip-flops are there. Flip-flop 0, flip-flop 1, flip-flop 2, flip-flop 3. That is 4 flip-flops are there. First, we know that for every clock pulse, Q0 is changes its state or it toggles. So J0 and K0 is connected to high. Then this is the output of Q0. This is a synchronous counter. So we are a single clock pulse is given to every clock input of the flip-flops. Then second, Q1 changes when Q0 is equal to 1. On the next clock pulse, Q1 changes. Whenever Q0 is equal to 1, then on the next clock pulse, Q2 changes. So here, this previous clock, Q0 is 1, then next clock pulse, Q1 changes. So on the last clock pulse, we are checking that Q3 is also 1, 0. Then only Q3 is 0, then only this changes of Q1 is possible. Whenever Q3 is 1, here Q3 is 1 and Q0 is 1, at that time on the next clock pulse it will not change. Only when Q3 and Q3 is 0 and Q1 Q0 is 1, then only on the next clock pulse Q1 is changed. So here we are providing Q0 output to the AND gate and also Q3 0, that is Q3 bar. We are selecting the Q3 bar, that will be input of the AND gate, and that AND gate output will be given to the input of J1 and K1. Then it will be provided Q1 output. Then next case, Q3. So when Q3 change Q2 changes, when Q0 and both Q1 are equal to 1, that time on the next clock pulse Q3 changes. So here it is Q0 and Q1, both outputs are 1. Then on the next clock pulse Q2 changes its state. So here we are taking Q0 and Q1 output. Q0 here, this is Q0 and Q1, this is Q1. Then both inputs are 1, then that output AND gate output of the AND gate is given to J2 and K2. So based on this stage AND gate output, J2 and K2 changes the state of Q2. Then next one is Q3. Q3 changes when Q0, Q1 and Q2 all are 1. Then it changes its state. So here Q0, this and Q0, Q1 here. Here this is Q0, Q1, that is taken given here, and Q2 here. Then here this is Q2, Q1, Q0 plus, then this one, this is connected to Q0, and here it is connected to Q3. So Q3 and Q0 both are 1. Then any of these condition satisfied, then it is connected to J3 and K3. Then any one of these conditions satisfied, then Q3 changes its state from one state to another. So this is the synchronous decade counter. Based on this equation, we are draw the synchronous decade counter. That's all about 4-bit decade counter.